Okay guys, Assalamualaikum and very good afternoon. There are some requests from your friends for me to repeat chapter 1 and go through step by step of the calculations and show the difference between the least square and the recursive least square. For today's video lecture, this is what I'm going to do today. Okay. The DT least square is a basic technique for parameter estimation. Before this method is described, some of the important notation are defined. K is a discrete time index. UK is the system input at discrete time K. YK is a measured system output at discrete time K. Theta K is the unknown parameter vector to be estimated. Theta hat K is the estimated of theta K. Phi K is the vector of input and output signals and possibly their delayed signal. Zeta K equal to Yk minus Y hat K is a residue. Y hat K is the estimated output signals. In general, this method finds the most probable value of theta K denoted by theta hat K, such that it minimizes the sum of the square of the residuals zeta K and minimizing the cost function J. There are two ways of estimating parameter using least square algorithms. Number one, offline least square estimation or batch processing. Number two, online least square estimation or recursive least square RLS. Offline batch least square estimation. Offline least square estimation can be used to estimate system parameters when at least a set of input data into the systems and a set of the corresponding output data are available. Consider the discrete time transfer function yk over uk equal to b naught plus b1z minus 1 plus b and bz minus nb over 1 minus a1z minus 1 minus a2z minus 2 minus a and az minus na. That can be written as yk equal to these equations. So you can arrange from this equation to this equation. Okay. The equation from the previous slide then arranged in the regression equation form as follows. Yk equal to yk minus 1, yk minus na, uk minus na, and b times a1, a and a, b1, b and a. So we get yk equal to phi transpose k theta, where here is the phi transpose k, and here is the equation, the matrix for theta, where yk equal to y hat k. Theta k is determined such that the output calculate from the right hand side of this equation, y hat k equal to phi transpose k theta match as closely as possible with the measured k in the sense of the least square. This is done by minimizing this equation, where n is the total number of data available for estimation, and En is equal to Yn minus Y hat n equal to Yn minus Pn theta. Therefore, En equal to zeta 1, zeta 2 until zeta n, while Yn transpose equal to Y1, Y2 until Yn, and phi n equal to phi transpose 1, phi transpose 2 until phi transpose n. So J is minimized by expanding the quadratic function, finding its derivation, and equating it to 0 to find the minimum point dj over d theta equal to 0. And this will giving the equation that we already derived in our first lecture, theta hat ls equal to phi n transpose phi n minus 1, phi n transpose yn. Okay. Okay, this is the example for batch or offline least square. I will give a PDF file. Please go through, and if you have any question, feel free to ask in the Telegram group. Okay, so next. Okay, type number 2, online recursive least square estimations. In online processing, the parameter is estimated in a recursive manner as the observations are obtained sequentially. The recursive least square algorithm is developed based on the batch processing algorithm using symmetric manipulations. This significantly reduces computational time and effort since there are no matrix inversion involved. Also, since the estimation can be done at every sampling intervals, it allowed the tracking of any change that might occur in the system. RLS can be used to estimate parameter of a transfer function in an online manner where the estimated parameter are updated at every sampling intervals. Okay, consider a discrete time dt system in the form that can be written in the regression models. Okay, yk equal to yk minus 1, yk minus na, uk minus nb times a1, a and a, b1 until b and b. So we rearrange the equations and we get yk equal to phi transpose k theta. Okay. The regression equation from previous slide then used in the recursive least square algorithm, whose summary is given in these tables. Okay, we have theta k, where is a current estimate is obtained by adding a correction to the previous estimations. And then Lk, L is known as the least square weighting factor, which tell how the correction and the previous estimate should be continued. Zeta k, the current estimation error. And the last one is pk. P is the mark that is proportional to the variance of the previous estimation, and rho is the forgetting factor that determines how fast all data are forgotten. If a rho is 1, so no data will be forgotten. Therefore, if the parameters to be identified are time varying, rho should take a value less than 1. The smaller it is value, the faster all data is discarded. We also assume theta hat 0 equal to 0 and P0 equal to sigma squared, with sigma squared are a very large number normally used. You can find it in the assignment question. Okay, P naught equal to metric 100, in that matrix identity 100. So this data will speed up the convergence process of the estimates to their true values. Okay, the reason why P naught is the very large number. Okay, so this will speed up the convergence process to estimate their true values. Okay, again, I will discuss an example for online recursive least square in the separate document. So please go through the example for least square offline or batch least square, and example 2 for recursive least square. Okay,